Hi class, welcome back to Electromagnetics. So we're starting a new section with this lecture. Last section we ended by introducing the distributed circuit model and how that leads to transmission lines, the definition of transmission lines. So now we want to take some time and do some transmission line analysis. And we're going to do this from two different perspectives. We'll do it from the frequency domain and the time domain. So this lecture is meant to initiate this discussions of the frequency domain. We'll start with a quick Bible verse, thought for the day, Matthew 7:13 through 14. Enter through the narrow gate, for wide is the gate and broad is the road that leads to destruction, and many enter through it. But small is the gate and narrow the road that leads to life, and only a few find it. So I think this is an important scripture from the Christian's point of view, in that there's many different avenues out there, at least advertised, for ways to come in communion with God. But to the Christian, there's only one true way, and that's through Christ. And so this is, I thought it was fairly applicable to looking at frequency domains, especially we start looking at narrow frequency bands and filters and that sort of thing. So a little bit of a stretch for correlation there, but I think it's applicable. So again, we're starting part 7 of the course, transmission line analysis. And so the first 4 lectures will be looking at frequency characteristics of and issues with transmission lines. And then we also want to take a look at some of the issues and aspects from the time domain as well. So in the previous chapter, or previous section, we introduced the transmission line equations, which are as follows. These two equations here, and hopefully by now you can recognize that this really is Maxwell's equations, just in a different form. And the biggest changes here are that we've substituted for electric field and magnetic field voltage and current. So they are analogous. So if we put a constraint on our analysis, this is what electric field actually translates to as voltage, and magnetic field to current. Primarily here because you can't have a magnetic field unless you have a time varying current. So that's why this is almost an even swap there. And likewise, hopefully you'll recall from your earlier circuit analysis courses that inductance and capacitance really don't play a factor in our circuits unless we have time varying current and voltage. And so there's where we see that come into play here as well. So hopefully you're starting to see that we are starting to make full circle here with things you learn in circuit analysis. But in this class, we start with Maxwell's equations and work our way through up, so you can kind of see what's going on under the hood, so to speak, to have a better understanding of where these equations came from and how they work. So for sinusoidally time-varying fields, we can change to phasor notation. So when we do that, that allows us to take advantage of some of the Fourier transformations, and so we can in place of time derivatives, we can add the j omega terms, and so that's what we've done here, just as we did in our earlier lectures when we were solving Maxwell's equations for the general case. So with this, we can now do some rearranging. If we were to take the second derivative here with respect to z, you would see that this I, our current term, would then be the partial derivative of I with respect to z, which is what we have here. So we can substitute this back in. So this whole term here, we substituted here for our derivative. We have a second derivative over here. So we remember from before, though, that we've redefined this argument of the voltage product as gamma squared. Again, where gamma is defined as the square root of this product here, which we have from here. And when we do that, then this allows us from differential equations to use the general form for the solution to this wave equation, which is just some arbitrary constant A times e to the minus gamma z plus b e to the gamma z. And for the current, same thing, except we have to divide by the intrinsic impedance of the material, or the dielectric. So we can rewrite this then with this Z naught term up there, where Z naught, again, is this characteristic impedance, and we define that as this term here. And so it's in terms of our per unit values of inductance, capacitance, conductance, capacitance, and inductance. So for the special case of a lossless line consisting of a perfect dielectric, then we'll have the condition where our conductivity would be 0. If it's a perfect dielectric, there will be no real current flow. So in this case, this simplifies our equation. Our gamma term becomes this, and the characteristic impedance then simplifies to this equation here. And the phase velocity finally is what we've seen before, just 1 over the square root of the permittivity times the permeability. And so this is pretty handy, because now we can define or calculate our intrinsic impedance by just our per unit values of inductance and capacitance.